Okay. Okay. So welcome to the final session of today. As our first speaker, we're honored to have Professor Sumeetpal Singh from University of Cambridge, where he's the head of the signal processing and communications group. He will talk to us today about bias-free particle filtering yeah, you can start sharing now, sorry. So he will talk to us about bias-free particle filtering for a continuous time hidden Markov model with the Cox process observation model. So welcome, the screen is yours.
Okay, thank you so much. Okay, so thank you so much for the invitation. It would have been great to be there in person, but unfortunately it coincides with examination period here. And for that reason, we really can't be away. Okay, in any case, so the title of my talk today is about bias-free particle filtering, and I'm going to deal with estimation of hidden Markov model. And in particular, the hidden Markov model has a continuous state and observation process. And the observation process is a type of process that is known as a Cox process. Essentially, the state is modulating a Poisson point process on the real line, and we're getting information, and we are getting observations that are triggered by the arrival of observations from this Poisson point process. So this is joint work with my PhD student Ruyang Jin, and also collaborator Nicholas Chopin. So this is the table of contents. So just want to check, is the size of the slide appropriate for you, or should I make it bigger or smaller?
It's good.
Okay, thank you so much. All right, so this is the table of contents. So I'm going to spend a bit of time on the application that really motivated the study. I'm not so much an expert of the application, but I think it's an application that is extremely important in the life sciences, and for that reason, I think it's worth looking at it in a bit of detail. And then we'll look at also the modeling that is behind this data set that this application has produced. And then this modeling will really set the scene for our inference problem, which is this continuous time hidden Markov model with this Cox process observation process. And then I'll tell you about particle filtering and how it's been applied to these kinds of problems. What are the shortfalls of present efforts? And then I'll tell you about the role of unbiased estimation in particle filtering. So this is quite an old idea, but I think we've revisited in the context of a new application, and perhaps are we able to say a few more new things as well, even for the methodology. We'll have to estimate something called a path integral. You'll see the mathematical definition of it. This is the cause of all our trouble, and we'll come up with some unbiased estimation techniques for this. And then I'll tell you about, in what sense is this algorithm difficult to tune, if at all, and I'll show you some numerical illustrations. Okay. So here's the motivating problem. So what you're looking at here on the left is an image of a live cell, and under a microscope, and the cell is live, it's imaged under the microscope, and they capture a video of molecules on the cell that are fluorescing. Now they engineer the cells so that certain biomolecules fluoresce when they're radiated with, when they're excited with a laser light at a particular frequency. And they get these grainy images over time. So this is an image at a particular time, say T15. And given these images, then they try to uncover the motion of those molecules on the surface of the cell. And that informs the biology they're actually studying at that time. So for this image, these, as you can see, is a very grainy image. There are some bright spots. So this could be one fluorescing molecule here, another, and so on. So there are quite a few of them. We don't know how many there are. And also each molecule is believed to take some sort of, so this is not a real trajectory, this is a simulated trajectory. Each molecule is believed to take some sort of diffusive trajectory like that. There may be a drift as well. So we're looking for the trajectory of molecules that produce these images. So the two estimation aims, and I'm going to focus on the first one. If I were to be given a sequence of images like that, I need to estimate the likelihood. So the likelihood is just a marginal distribution of the data. And the reason why we need to estimate the likelihood is we want to be able to calibrate the model. Okay, so the model has got many parameters that need to be calibrated for the real experiment. Okay, and then as a secondary objective, you want to estimate the trajectory of the molecules that are generating the data. So I'm going to focus on the first objective, which is to compute the likelihood. We're going to estimate it, and we're going to use it to calibrate the model. And here's a caveat. So although I've shown you a real image, I'm going to use a model which is what I call an idealized model of detection. Okay, we're going to see the mathematical definition of it. It idealizes the image generation process, and still it throws up a lot of challenges. Now it's still relevant for various reasons, and we can have, if you want to quiz me on that, feel free to quiz me, but otherwise we'll just proceed with the caveat that in what I'm going to be speaking about, I'll be using an idealized model of detection. Okay, but still there are quite a few difficulties when one deals with this model itself, although it carries the name idealized. Okay, so like I said, these molecules that are diffusing in the cell, these biomolecules that are tagged and fluorescing and diffusing, we assume that they have a 3D location. So, and it follows diffusive motion. So xt here is a three-dimensional vector. The first component and second component could be the location of the molecule on the surface of the cell, is xy location. And the third component could be the depth of the molecule. So these cells are 3D objects, and the molecule can reside at various depths in this cell. So here we're going to see a model that looks like that, which is SDE with a linear drift term and driven by Brownian motion. And I mentioned what these coordinates mean. And I should say that it's not a simplification inspired by Earth. This model is actually very widely used in single molecule fluorescence microscopy. So in the absence of another type of more exotic diffusion, they often assume the molecules move according to a motion model like this. So this is not really, in any case, a simplification just yet. Okay. So here is a simulated trajectory of two diffusing molecules. They're diffusing about some mean location. One's a green molecule, sorry, one's a blue molecule, one's an orange molecule. Okay, this simulation is not so important. What's important from our assumption of the linear SDE model is that we can simulate its motion exactly. So by that I mean, if you give me the location of the molecule at a particular time, t1, and you want me to find this probability distribution at time t2, then I know it's given by a Gaussian distribution with a particular covariance matrix and a particular mean, which is given by phi times x plus a. And under the assumption of a linear SDE, we know how to compute phi, a, and r exactly. They have known forms. So this is the setting I'll be working with. So just to remind ourselves, the molecule diffuses according to a linear SDE. We can simulate its skeleton exactly. So what's the motivation for this SDE? Well, firstly, they assume these molecules have diffusive behavior because they want to cope with any amount of observations. So they can generate observations at very fine time intervals, very closely spaced observations in time, or they can generate them sparsely spaced in time. So this is something the experimentalist has control of. And so therefore they need a model that naturally interpolates between all the extremes. So that's why it's a continuous time model is appropriate. Now linear, because we want to be able to exactly simulate the skeleton. And like I said, very rarely do they assume a model which is nonlinear unless they have strong reason to believe it follows a more exotic motion. Okay, so now I'm going to tell you a bit about how the data is generated before we move into the computational methodology. So here is the data. So our data is a sequence of time of arrivals, T1, T2, and so on. So T2 is larger than T1, T3 is larger than T2, and so on. So T1, Ti is the arrival time of the ith observation. And then associated with each arrival time, we have a particular observation, yt1 for time t1, yt2 for time t2. And this is a two-dimensional vector, which is a noisy observation of the location of the molecule. So remember, the molecule has three coordinates, its depth and its x and y location. And y will give us a noisy observation of the location. And then the natural question arises is, what about x3? What about its depth? Do we observe it at all? Well, yes, we observe it indirectly, as I will explain next. We observe it indirectly through the time of arrivals and also through the variance of the observation. And I'll tell you more about that in the slide to come. So how are the time of arrivals generated? Well, it follows a Poisson process on the real line. So what I've done here is I've illustrated some time of arrivals, T1, T2, and this is the ith time of arrival. And so now we are contemplating the existence, the occurrence of an arrival in this small interval delta, on the assumption that the arrival process is a Poisson process. On the real line, the probability of getting an arrival in small interval t to t plus delta is independent of everything that happened before it, and it's going to be proportional to the intensity lambda times the width of the interval. So the most important thing is this intensity. It seems to suggest in this picture that the intensity is independent of the state of the molecule. That's not true. It will be dependent on the state of the molecule. And we'll see precisely in the next slide how it's dependent. Okay, here is an image that illustrates the experiment itself, how they gather this data. So what I have here is a biomolecule that's tagged, and you don't see its location in the X and Y plane. You're only observing its depth in this image. So it seems to be diffusing about some mean depth mu, like this. And I'm keeping track of its depth in the medium. In the medium it diffuses in. And these molecules are excited to fluoresce. And every time they fluoresce, they mean they create an observation. And these observations, and so how does this fluorescing process work? Essentially, they excite they excite the molecule with a laser, and the laser undergoes total internal reflection here. But still, there is an evanescent field that is created, and that field penetrates into the depth of the sample, and but decays exponentially in depth. So the excitation of the molecule follows an equation like that. Lambda naught is the intensity of the field, the excitation of the laser at depth 0. And then as the molecule gets deeper, the amount of laser light that reaches it decays exponentially according to minus beta times its depth. Okay, and this is going to be the intensity function that we will use for the arrival of observations. Okay, for the time of arrival of observations. As you can see, all that defines the time of arrival of observations is the instantaneous location of the molecule, and not its X and Y location, it's just its depth. Okay, and so there are many tunable parameters in addition to the motion model of SDE, which is not known and has to be tuned for the experiment. What is also needs to be tuned is this depth, is this intensity at depth 0, and the rate at which the intensity decays as a function of depth. So we call theta the static parameters of the model that we have to find that best describes the data set. And so we augment whatever we had for the motion with more parameters to do with the intensity of the excitation laser as a function of depth, which is just lambda naught beta. Okay, so now I'm going to tell you something more about the observations. I've told you about how the observations, at the time of arrival of observations, let me tell you a bit about the how the location of the observations themselves. So here I have a simulation of a molecule that's moving from the top right-hand corner to the bottom left corner. So the passage of time is illustrated with color. So a dark color means later, time further back in the past, and light color means more recent time. These are examples of this is a simulation of observations that you could receive. So I'm not showing the time of arrival of the observation. I'm just showing you the location of the observation. As you can see, the molecule moves from the top right to the bottom left. The observations are just noisy noisy positional values for the molecule. So they kind of track the motion of the molecule. But we're going to be working with a 3D model for generating observations. So because the molecule is moving, it can move in and out of focus. And the appropriate model for a molecule that changes depth, which means it's moving in and out of focus, is an observation process that looks like this. As you can see, this observation process is highly scattered because the molecule was perhaps out of focus. And so on. It still seems to obey, you can still see the time of arrival of the observations according to the colors, but it doesn't have doesn't cleanly follow the trajectory as you have. So this model is known in the literature as the Born-Wolf model, but the name is not particularly important. We're going to use this model in particular. Okay, so I've just shown you what examples of observations look like, what YT looks like. Let me just describe this now slightly more mathematically, but still a bit abstract. So when the time of arrival has been determined, then you need to generate the numerical value of the observation. Okay, the value of the observation is been assumed to be sampled from a probability density function G, which depends on the location of the molecule in the XY plane and its depth. Okay, because the depth controls whether the molecule's in focus or out of focus. So here are plots of what G looks like as a function of Y. So G is a density in Y for any given X1, X2, and X3. So if you integrate G over Y, it integrates to 1. When the molecule's in focus, you get a very nice peaky observation density around the location of the molecule. And as the molecule goes out of focus, the observation density starts getting more spread out. And this annular rings actually comes from diffraction theory. So these observation models are built from the physics that underpin how photons are captured on the detector. So now we can augment theta, which is the motion model parameters, the parameter for the intensity of the observed process, with now some more experimental parameters. And the relevant experimental parameters would be the emission wavelength, some parameter to do with the microscopy instruments itself, the refractive index. Now, these values are known, and you may be wondering, why am I augmenting known values with theta and pretending they are known? Well, in most cases, they know quite well the relationship between the observed process and the hidden state as a function of theta, but at the end of the day, it is a model, and some small amount of tuning is needed for any sort of inaccuracy in the production of the model, in the actually translating the physics into a model for G. Okay, so you still need to estimate these, although you have strong guidance on what some of these parameters are, but not others. Okay. Okay, so now here's the inference objective. So theta is a vector value parameter. How many parameters there are depends on the experiment. It could be 10, 15, 20, depending on the number of molecules as well. Let's just assume there's a single molecule. Okay, so if I knew theta and I knew the exact trajectory the molecule took between time 0 and capital T, then I can describe the probability density of this data set. So here's my data set. I've got n data points recorded until time capital T. And this is what the probability density of the data looks like. It's a product of terms, and I'll explain to you each term separately. This accounts for the observation, YTI given XTI. This term accounts for the time of arrival TI rather. So as you can see, the deeper the molecule, the more unlikely it created that time Ti. And this term accounts for this is an exponential of an integral between Ti and I plus, and Ti minus 1 and Ti. So that's a silent period when we observe nothing of the intensity function evaluated at the location of the molecules. This is what we call a path integral, an integral over the path of the diffusing molecule from time Ti minus 1 to Ti. We need to exponentiate and put a negative number and negate it. And we have one such term for every observation interval. Okay. And it accounts for the silent periods between observations. And it is this integral that makes the evaluation not possible. And obviously we don't observe X, we don't know what X is. So we need to integrate over X according to the diffuse SDE model, the molecule that describes the motion of the molecule. So the marginal density of the data as a function of theta is given by this expected value. So I've capitalized X to indicate they are random variables now. So all these terms, the product of these terms are all there. And these product of small path integrals, because there is one for each inter-arrival interval, you can actually combine all of them into a single path integral from time zero to capital T. Okay, so this is a combination of all of them. So the likelihood is, we want to be able to compute this likelihood, and we can't evaluate this likelihood precisely because of this path integral. Okay, so we need to deal with this problem. So what I said before was that exact calculations of the marginal density of the data given theta, or the likelihood of theta, is not available for a moving molecule. Okay, and this is a problem that experimentalists are faced with. So those who routinely deal in the analysis of microscopy data, they need to be able to compute L theta. But they know how to compute L theta if the molecule is static. So if you assume the molecule is fixed, doesn't move from time 0 to capital T, then the likelihood collapses. That path integral just becomes, exponential of the, essentially, it collapses something which is very easy to estimate. I mean, there's no problem computing any of this. So if the molecule was static, they can compute the likelihood. If it's not, they can't. Okay, so we need to deal with the case where the molecule is not static, and I'll tell you how we compute the likelihood. Okay, so if you know about particle filtering, you will be tempted to apply particle filtering to these kind of problems, and they have been applied. Okay, and there are a few niche groups that deal with this, and let me tell you a bit about the idea that underpins their implementation. So firstly, let's just discretize time 0 to capital T into intervals of size delta. Okay, so I call T0 delta time 0. Let's say there are m intervals of size delta. So Tm delta is time capital T, and then these are all the times in between that. And roughly, this discretization is uniform, just that I narrow it so that I make sure it coincides with the arrival of the real observations. Okay, so the real observation times are a subset of this. This is a bit of a detail that's not important for what I'm saying. That's not too important for the gist of my message today. So if you were to discretize, if you were to define a time discretization, then I could also discretize the likelihood. So there's no discretization here. It is the path integral on the discretized. So where I had the integral, the exponential of the integral, I'll replace the exponential of the integral by just this Riemann approximation. So it's just the value of the intensity at the particle at time Ti delta times the interval between the length of the interval between Ti delta and Ti plus 1. Exponentiate that, and this is a simple discretization of that continuous time model. And once you see something like that, you can simulate the skeleton of the process X at every time T1, T2, and so on, T3 delta, and so on. Immediately you'll say, right, I can actually apply a particle filter and give me an unbiased estimate of this. So this we have to be careful. This is biased because of the discretization. Okay, but that doesn't mean a Monte Carlo estimate of this is going to be unbiased. Okay, a Monte Carlo estimate of this expectation, a good high efficacy Monte Carlo estimate doesn't necessarily have to be unbiased, but it is. Okay, a particle filter can unbiasedly estimate this quantity here, but it cannot remove the bias in the discretization of the model. Okay. So here is the particle filtering algorithm for unbiasedly estimating the discretized likelihood. I'm not going to go through the algorithm in detail, other than to say, for those of you who know particle methods, all I'm trying to highlight here is the fact that what the weight is in the resampling step of the particle filter. For those of you who don't know particle methods, well, you can say that I'm simulating a population of values for the state at time t0 delta, t1 delta, and so on forward. I'm going to use importance sampling to reweight the state every time I have an observation, and then I'm going to use resampling to sample that weighted population down to an unweighted population to stabilize the algorithm over time. Okay. So the weight is as follows. The source of the bias in the weight of that you assign to each of the samples as you simulate them forward from time 0 to capital T arises because of this discretized approximation of the true path integral. And those of you who know particle filters well, you have to be careful when you simulate a particle filter when the time discretization becomes narrower and narrower. So what I use is, what I use is for resampling is the systematic resampling algorithm, which is known to be stable as a two-time discretization. And I can tell you more about that if you have any questions. Okay, so this is a simple algorithm to do. It involves simulating state values forward and reweighting them and resampling them. And once you've done this from time 0 to capital T, which is you need to visit every discretization time T1 delta, T2 delta until the final discretization time, which coincides with capital T. And then you collect your important sampling weights, and you form the simple estimate, which is the product of the weights you created from time 0, product of the average of the weights you created from time 0 to capital T. And this is well known to unbiasedly estimate L delta. So this is an old result, nothing to do with the fact that the algorithm runs in continuous time. It's just a result for discrete time methods. The particle filter will produce an unbiased estimate of L delta. So L hat delta, the expected value of L hat delta will coincide with L delta when we take the expectation over the realized law of the particles. Okay, and this result goes back to Pierre del Morel many years ago. But there is a trade-off. And what is that trade-off? Well, there is a trade-off in choosing delta. Okay. And let's look at what this means. So I'm interested in computing. I know this is biased, so I want to compute the mean square error of the estimate. So I want to subtract from the estimate the true value, compute this mean square error, and I'm just rescaling it by the true value. Okay. So I'm dividing by the true value. So we all know that the variance bias decomposition. So this mean square error has a term to do with the variance, which is the number of Monte Carlo samples, and the bias to do with the discretization of the path integral. And that bias is of the order delta square. And there are some constants here, C2 and C1. I don't know what they are, okay, but they are there. But it just shows the relationship between the MSE, the discretization interval, and the number of samples, Monte Carlo samples you simulate. Now, if you give me a fixed computational budget, fixed CPU time to use, and I call that calligraphic C, then I can convert this into a relationship involving the CPU budget. Well, I know I have to simulate n particles forward for T over delta time steps. So I can convert n into a relationship involving delta and the CPU budget, and I just wrote it like this. Now this allows me to do to find the best delta for my CPU budget. It's not practical, but we need it so that we compare this trivial method in its most favorable context with the method we are going to propose. Okay. So first thing to do, like I said, the variance plus bias relationship has this form, is 1 over delta plus delta squared times some constants which I don't know, but by CPU budget obviously I know. So the first thing, let's confirm this relationship with some numerical work, and then we'll look at what happens when you find the best delta. Where did that go? Okay, so assuming this relationship is true, before I show you the numerical result, assuming this relationship is true, we can obviously differentiate it with respect to delta and find the best delta, and that will give me delta star, and it will say that the mean square error decreases with our CPU time, like C to the power of -2/3. Okay, this is what we'll end up with. If we did not have a bias, then we wouldn't have the term to do with the bias squared. If we could get rid of it, of the bias for some discretization interval delta, then obviously our mean square error would decay like 1 over the CPU budget. This is what we aim to do, okay? And this is what we have with the naive discretization method, okay? So here's a numerical result confirming this relationship of 1 over delta plus delta squared. So what I've done here is for a given CPU budget of 1.5 seconds, we simulated the relative MSE. We computed the relative MSE for various choices of delta. The crosses represent the true, the numerical value of the simulation. And this solid line is just interpolation. We fit the best 1 over delta squared term. And the dotted bits are just basically, I don't interpolate, I don't fit a relationship outside, too much outside the local minimum. Because I'm interested in this delta. This delta is the best delta for that CPU time. So now, if we every time we have more CPU time, we simulate the relative MSE for various values of delta. We find the best delta, and we run the estimation technique with the best delta, and we'll see what our best MSE is as a function of CPU time. Remember, I said it decays like this. C to the power minus 2 over 3, and this is indeed confirmed in numerical implementation. This is the best MSE you can get for any CPU time, and that's the dotted line is the fitted relationship we knew should hold if the in theory that informs this is correct. Okay. But this is not a practical method, okay? It's not practical to hunt for the best delta every time you have more CPUs. Highly impractical, but it's just to show this method in its most favorable setting. Okay. I got about half an hour. Is that correct, or less?
There's about half an hour left.
Okay, that's fine. I won't take up all their time. I think we are more than halfway there. Okay, so now I want to get rid of the bias. So I'm going to talk about unbiased estimation in particle filtering. So I'm going to stick with the same time discretization, T1 delta, T2 delta, and so on. I'm going to rewrite the exact likelihood using these discretized intervals. And so I had a path integral from time 0 to capital T. Now I collapse it down into a product of m different path integrals. Okay. Given by these exponential terms. Now, this is what I want to estimate, but I can't compute this because this involves it's simulating the diffusive motion in its continuously from time in between these time instances, T delta J minus 1 and T delta J. So what I'm going to do is introduce a model with unbiased estimation. So wherever I see an exponential for a particular exponential or path integral for a particular interval, I am going to replace it by a random variable EJ. So EJ for E1 for interval from T0 delta through T1 delta to, let me check if the time to start at 1 or 0. Let me just check. Sorry for that. Okay, at 1. So E1 for the first interval from which is defined as T1 delta to T2 delta, E2 for the second interval with T2 delta to T3 delta, and so on. Okay. Now I want these random variables to unbiasedly estimate these things, these path integrals. So expected value of EJ, given the value of the process at the start and the end of the interval, should correspond to the path integral we want. And for the sake of convenience, I want also for the convenience of the implementation, which is not really a restriction, I want these random variables E to be conditionally independent given the skeleton of the continuous time process at the times T delta. So that means the joint probability density of E1 to EM given the skeleton is just a product of the probability of their probability densities. Okay, conditioned on the end and start points of the relative interval. So this is the conditional independence assumption. Okay, so now, how do we create, how do we define a model like this? Okay, so here we're going to go back and dig into perhaps a lot of work that was published about 10 to 15 years ago by Alex Beskos and colleagues. They had looked at these kinds of problems. And I'm going to revisit their estimator and hopefully tell you something new about it. So let's just say you want to compute the exponential of an integral of this form from 0 delta lambda xs ds. Okay, and I put it in blue for a specific reason. So I'm going to call this I. So I is this negative of this integral. So I can subtract a constant times a constant, add a constant. So I subtract c and add c, so that just comes a product. And c is going to allow me to tune the estimate, so I need to introduce it. Now for exponential I minus c, I can expand it using this geometric expansion. So it's I minus c to the power k over k factorial. There are too many terms in this, so I can introduce importance sampling so that I don't have to evaluate an infinite number of terms here. So I introduce a Poisson probability mass function with rate eta. So this becomes this now. And then for each, for each of these products involves an integral, and I really cannot do this continuous time integral. So what I do now is I approximate each I in this k product, there are k separate approximations of I and E. I approximate it by essentially sampling a uniform number between 0 and delta and evaluating lambda at that uniform number. Okay, and that will give me an unbiased estimate of this integral. So I've replaced I here with the value of the state at a uniform time tau I between 0 and delta, appropriately scaled, and I evaluate lambda at x tau I. And so this is all equality, so I can write it now in one single form, which is as follows. This path integral is also the expected value of this term here. We generate kappa according to Poisson probability mass function, which tends to be eta. And for that value of kappa, you sample tau I independent uniform numbers between 0 and delta, simulate the state process at that tau I. Remember, we could simulate the state process at the skeleton, and you form this product. Okay, and that will give you an unbiased estimate of what. So in summary, the estimate of the exponential of the path integral is given by this product. So if we go back to the previous page, there was a C here. Now I've committed myself to a specific choice of C, and that results in an estimator that looks like that. The specific choice of C is not too important. But what's interesting here is when I write it like this, is you can see in the naive implementation by just discretizing the model, we only have this term, right? Now we've got all these terms to do with the Poisson simulation and the uniform time simulation between 0 and delta, and the simulation of the skeleton of X at that time, tau I, that serves to correct for the bias of just retaining the simple Riemann approximation. So to generate this random variable, you got 3 steps. You simulate a Poisson random variable according to eta for each. Then you simulate independent uniform random numbers between 0 and delta. You simulate X at tau I. You evaluate lambda at x tau I, and then you can form this estimate here. It's an unbiased estimate of what you want. So this is an old idea. It comes from Beskos and colleagues, and in fact, maybe even predates them. And I think they talk about where these ideas, what was the genesis of ideas like that? Okay. All right, so I'm going to tell you a bit of starting to touch on our contribution. I know I'm a bit slow, but it's fine. We get as far as we get. So this specific choice of C is not so important. It's important detail, but not for the main message. So I said that this estimate is what we had before plus some terms. What I'm going to do, these terms only appear if kappa is non-zero. So if somehow this step reduced positive value of kappa, it can reduce 0. So therefore, what I want to, and this estimate actually, although it's unbiased, it can be negative because there is no guarantee that this term here, when scaled by delta over eta, will be smaller than 1 in absolute value. There's no guarantee it can be negative. So it can, so 1 plus this can be negative. So this estimate can be negative, and that causes a problem with particle mechanics because a negative weight is not something which is something you sample with. So what we're going to do now is we're going to have strong control over the negativity of this estimate. So this estimate is only negative and kappa is positive. So we need to control the probability the estimate is negative, conditional on the fact that kappa is positive. Okay, this is what we need to be able to control. Okay, so let's think about, could this actually be negative? Well, I said it can, because there's nothing stopping this whole thing to be a number smaller than -1. But it's unlikely. It's unlikely if delta is small. And the reason is, the most negative this can be is when this is at its largest times -1. And if you assume lambda is Lipschitz, so I'm just put delta over eta there, the Lipschitz constant for lambda is L, and the largest negative value this can take is minus L times the maximum excursion of X between in the interval 0 delta, and we know this will be of order square root delta. Okay, so the idea is as follows. If I choose eta to be some constant times delta, then I have strong assurances of positivity of this estimate. And that's what I'm building my technique. Okay, strong assurances, what does that mean? Okay, before we go into that, let's look at what we actually end up doing. So for particle methods, I said I'm going to introduce estimates of these path integrals, and I told you they can be negative, but I told you it's unlikely they're going to be negative. So what I'm going to do is I'm going to introduce a truncation of the weight. Just keep the positive part. In the rare occasion it's negative, I just force it to 0. Otherwise, I just keep it's positive. Otherwise, I just keep its value when it's positive. So in essence, we have introduced a bias because this is not the true weight. This is the truncation. So therefore, if we implement a particle method that estimates this unbiasedly, we have introduced a small bias to do with the truncation. But is that bias actually significant? It's not. Okay. But before I tell you that, let me just say that my algorithm, the algorithm that we conceive, doesn't collapse. Doesn't become, the cost doesn't blow up as a function of discretization. Because remember, we chose the amount of simulation to be proportional to delta. Okay, so the amount of simulation shrinks with delta, and the overall cost of the algorithm is simulating n particles forwards for t over delta time steps, because we discretize t into lengths of intervals of length delta, and this is the extra bit to do with the Poisson estimate. It's just a term which is of order delta. So if you multiply through, it has the same cost as the naive bias algorithm, effectively the same cost to it. So it doesn't blow up as a function of, so it doesn't blow up due to the Poisson simulation, okay, due to the Poisson estimate of the path integrals, okay, so because it has the same cost as algorithm 1 roughly. Okay, so we want to control the bias of this method. So first thing I need to do is find out how likely these weights will be negative. I said unlikely. So the probability of encountering a negative weight, we can have some exact calculations, but effectively it looks like this. The probability of encountering a negative weight from time 0 to the end time decays roughly like exponential 1 over delta. Okay, so it decays very quickly. Therefore, the bias of the approximation between L truncation and L, the square of the bias, is that what we want, or the mean square error, is of the same order, exponential minus 1 over delta. Okay, this term here doesn't cause us any grief. Sorry, this term 1 over delta doesn't cause us any grief because it's quickly subsumed by the exponential minus 1 over delta. Delta goes to 0, this decays very quickly. I could play the same game and optimize the MSE for a given CPU budget. Although I'm not going to do that because, like I said, that is not a practical algorithm, that's highly impractical. But if I did, my mean square error will decay as a function of CPU budget, not like 1 over C, like a truly unbiased method, but something fairly close, like log C over C. Okay, and you compare before it is C to the power 1 over C to the power minus 2 over 3. Now it's going to decay very much like an unbiased technique. Okay, subject to the log C penalty on the numerator. Okay, so I said I don't want to play any tuning game, but let's just say you did play a tuning game. Okay. If you had a bigger CPU budget, you have to find the best delta for algorithm 1. And that best delta can change a bit significantly because delta 1 over delta will increase like C to the power 1/3. Whereas for our method, because of the log C dependency, 1 over delta increases with CPU budget. The 1 over the best delta increases with only log C. So even if you double, triple the CPU budget, you're not going to change whatever tune delta star you found before. It's still going to work. But we don't advocate this tuning game. Okay. And this is the heuristic we do advocate and we do implement, and produces pretty good estimates. We advocate choosing delta and always choosing eta to be delta times the Lipschitz constant of the intensity function, so that the probability that an n particle system will encounter a negative weight is minuscule. It's so small. Okay, so let's say this was the bound we found. So we find we just have to choose delta because eta is fixed with delta times L, so that the probability of this is smaller than 10 to the power minus 6, say. So basically 1 in a million particles runs will encounter a negative weight. In fact, this probability decays so rapidly for sort of a practical number of delta, which coincides with the how high frequency real single molecule experiments are. If you choose delta to be 10 milliseconds, times say 2 seconds, 3 seconds, this is basic, or even 1 second. This is basically images are recorded for a couple of seconds because these molecules bleach very quickly. And say for 10,000 particles, the probability of encountering a negative weight with such a modest value of delta is of the order of 10 to the power minus 15. In fact, it's embarrassingly small. Okay, so it's really, really small. So you pretty much should never see any negative weight, and that makes us think that we know because the probability of a negative weight is related to the bias. So the bias is essentially non-existent, right? So okay, so we run our method. Remember, I said I needed an estimate of the Lipschitz constant of the intensity function L. We can estimate that sequentially without introducing any Monte Carlo bias. Okay, I'll skip details. And essentially we run both methods and we can see the C to the power minus 2 over 3 behavior for the best tuned naive algorithm. Whereas for our algorithm, we don't tune it, we just run it forward with our heuristic, and we can see that we achieve pretty much the mean square error decays with CPU roughly like 1 over C, because you're in the regime where bias is so small relative to variance that you're seeing the 1 over C decay. Okay. All right. So just a couple of more simulations. So this is the sort of data we simulated. So here's a molecule that's diffusing all over the place. The passage of time is again illustrated by color. Dark colors are the initial location of the molecule, and then the lighter the color, the location of the molecule later in time. So it starts here, diffuses, ends up here. These are the location of the observations we detected. As you can see, they're all over the place because the molecule is diffusing, and also the molecule changes its focus, goes in and out of focus. These are some estimates, not very important. Okay, what's important for this kind of data? Okay, so this is the only thing I want to say, and then I think you can end up with that. So remember, we can define a posterior over theta by combining the likelihood for theta with a prior. Okay, so this is the true posterior. It's proportional to L theta times P theta. We don't know what it is. The naive method gives us a bias posterior, which is the prior times the bias likelihood. And our method, which it's unbiased with, which is it's almost unbiased. So that's why we just say unbiased with in a small quote like that, just to say that it's a misnomer really. It's proportional. Our posterior is proportional to the truncated Poisson estimate likelihood with the prior. So we could simulate. We could visualize the shape of at least these two posteriors because we don't know what this is, except for for toy examples. We could visualize the shape of these two posteriors by running Markov chain Monte Carlo, and all you need to do is to have an unbiased estimate of this or this, which we know the particle filter gives us. Okay, so it's a very simple algorithm. It's due to Christoph, Andrew, and all. It's a direct paper in JRSSB. It's not a particle MCMC. Most of you will know. So if you want to generate Markov chain Monte Carlo samples from theta according to any one of these two posteriors, all you need to do is have unbiased estimates of the likelihood, and then you propose a new sample, you accept or reject using the usual acceptance probability for MCMC, and you just plug in your unbiased estimate of the likelihood. So this equation here is for generating samples from this. A similar one will generate samples from this, but you replace this with your truncated, our Poisson likelihood. Yeah. Okay. So here's 2 examples. The first experiment we're gonna, oh, sorry, what have I done? The first experiment is one where we have a low CPU budget. So this will force a large delta for our naive method algorithm 1. The second experiment is we have a high budget, CPU budget, so we can allow us a smaller delta. So we can find the best delta for the CPU budget according to the impractical tuning scenario we talked about. And our method essentially will work under low CPU budget or high CPU budget, not tuned in any way, we just calculate delta to make sure the probability of encountering a negative weight is minuscule. Okay, and as you can see, the light gray plot is our method under both high and low CPU budget. As you can see, under the low CPU budget, this naive method is fairly biased. As you can see, the dark plot is the posterior for some parameters. As you can see, it's shifted quite a bit. But if you have a high CPU budget, as expected, the naive method starts approaching the method we are proposing, and the bias is small, perhaps even negligible. But the most important thing is that our posterior for a small CPU budget and a high CPU budget effectively is unaffected. Okay, and it's close to the truth. In fact, it's extremely close. Probably not. I mean, it's not even the difference wouldn't be discernible. Okay. Okay. I think I can just say something about the last experiment. What's important in MCM? So we've got an MCMC algorithm targeting 2 different posteriors. One is this, and one is this. Okay. So we normally are going to run these MCMC algorithms for a fixed amount of time, and they will both generate. So we'll get samples from this, and we'll get samples from that. What's important is not the number of samples, but the number of independent samples we got, and we can measure that through the effective sample size. So we run the MCMC algorithm for both posteriors. The ESS is the sample size divided by something known as the integrated autocorrelation function. And it basically says out of that batch of MCMC samples, you have effectively this many independent samples had you thinned them. Okay. So if we need to tune the bias algorithm so that we can shrink delta to the extent that the ESS will match our algorithm, so it's a fair comparison. So if we have delta too big, there'll be too much bias, but the effective sample size will go up. If we shrink delta, the bias will decrease, but the effective sample size will decrease. So I just shrink delta, we shrink delta so that ESS is the same. And as you can see, even if you wanted to run this MCMC algorithm for a fixed number of time, and you fix amount of time, and for the same ESS, the bias method will deliver a slight verbose solution than our method. And this and how bad this is can depend on the context. Okay. Okay. So in conclusion, I think what we have is a simple and overlooked solution for particle filtering. Evaluation of likelihoods expressed as path integrals. So what I mean by that is that we've combined particle filter with an unbiased estimate of the path integral given by the Poisson estimate with negative weight control. The frequency of the weights of negative, we control it, and effectively we have a nearly unbiased method for estimating likelihood. Now, once you have unbiased estimates of the likelihood, you can effectively find the posterior using particle MCMC, and this is useful and impactful for single molecule experiments because they have a bias that they cannot quantify, and hopefully we remove it for them. So it's useful for them, and actually potentially it's useful also for inference in continuous time in Markov models, because when you have these path integrals appear there as well through a change of measure. Okay, I think I will stop here and take any questions you may have.
Thank you very much for this interesting talk. Do we have any questions from the audience here in KAUST?
Hi, Sumit. Thanks for the talk.
Hi, Neil.
I just have 2 questions. So my first question, maybe you stated it, but I wasn't so sure. the unbiased estimation that you've done for the likelihood, this was done for both the ARI models and also the Born and Wolf models. When you have those different observational models, it works fine in 2D and 3D.
Yeah, so the ARI is a model. So I'll just go back to that page. Okay. The ARI model assumes the molecules in focus. It is subsumed by the Born-Wolf. When the molecule is in focus, data basically collapses to the ARI model. When it moves out of focus, it departs from the ARI model. So by dealing with the Born-Wolf, you subsume the ARI model automatically.
Okay, thanks. And my second question is, the unbiased estimation methods you're using have been well known for 10 years or so from Beskos and others, but is there any way that you could have used more recently developed unbiased methods from Pierre Jacob or similar offers?
Yeah, so the problem is that, so the unbiased estimate from Beskos and all deal with this path integral. And essentially, you can't obviously integrate this continuously between 0 and delta. So the unbiased methods from Beskos and all is slightly different from Pierre Jacob, because Pierre Jacob is not dealing with path integrals of this form. The contribution that is different from Beskos and all is that Beskos and all recognize that this Poisson estimate of the path integral can be negative, and they put a lot of effort into coming up with alternatives that ensure the Poisson estimate is only positive. And this is a quite involved simulation technique. But what was overlooked by them, I think, and maybe the reason is because they didn't work in the small delta regime, is that the probability of seeing a negative weight is minuscule. And so really just a simple truncation, you have bias that is essentially unobserved. So there was no need for any of this more exotic schemes, which obviously would have benefits in a more broader context than ours. But here the idea is that if you can study the probability of finding negative weights and you can control it, you have a simple algorithm that is simple to implement by just about anyone, and it's more than adequate for the intended purpose.
Okay, thanks.
Okay, do we have any other questions from the room? Okay, Hamza.
That's good. Thank you. Thanks, Sumit, for the nice talk. I just want to make sure that I understand correctly something. So this scheme will result in a biased estimation once the Poisson estimate is negative.
Yes.
Is that correct?
Yeah.
So it's actually, the estimate is not 100% biased, but it's a kind of unbiased, but with a high probability, right?
It's correct. Yeah.
Okay, just want to understand that.
That's right. And in fact, you can, using importance sampling, you can correct for the minuscule bias when you see a negative weight. I need to talk about it, but that's not important because you are looking at ridiculously small numbers like that, the probability of seeing a negative weight. And the bias is of the order of the probability of seeing a negative weight times a constant, which is a function of t, but not large because t is 2 or 3. So, you can simulate this until a very, very, very long time when you not see a negative weight. So yes, it's biased, but it's biased, but so well controlled that effectively it's for all intents and purposes is good enough.
Another question about the particle filter.
Yes.
For estimating the likelihood.
Yes.
So to my knowledge, it's really hard to using particle filter in continuous time.
Yeah.
For estimating the likelihood without coming up with a creative way to resample. And so could you please elaborate on this? Like, how do you prevent the algorithm from collapsing?
Okay, so when you deal with the diffusion on a skeleton, okay, although the path integral is there, so this is the naive algorithm, remember? Although the path integral is there, the naive algorithm and our method essentially converts this to an estimation, to a discretized model, which is a hidden Markov model in discrete time. So particle filters can be used in this context in a simple way. Where the problem set in is what happens as discretization interval becomes smaller and smaller. If you use a naive particle filter like bootstrap and multinomial, sorry, the multinomial resampling operation, the number of resampling operations will explode as the delta shrinks more and more and more. So essentially, you end up with a useless algorithm. But in a recent archive paper with some colleagues, we studied the resampling operation of a particle method as a function of discretization, and we've got some results that for a few resampling operations, one of which is systematic. Essentially, it says that the resampling instances of the algorithm when it resamples will stabilize. So it will not resample at every delta. It resample basically. The discretized particle algorithm will converge to a continuous time particle system that jumps at random times to do with its resampling. Okay, and this jump times is not an explosive process. So you know you will see it, but with good amounts of time between one resampling instance.
Right. Thank you so much.
Thank you.
Okay, let's thank Professor Singh again for his nice talk.
Thank you.
Okay, so for the final speaker today, we're happy to welcome back Professor Matthias Sunbury from KTH in Stockholm. He's a long-term collaborator with the Stochastic Numerics group here in KAUST and a frequent visitor to KAUST since 2009-10 or something.